Hey everyone, welcome to This Explainer. Today, we're diving into a really fascinating argument from Yann LeCun about why our current massive obsession with scaling large language models might actually be a dead end for true physical world intelligence. Look, the commercial success of LLMs is undeniable, right? I mean, they write our code, they draft our emails, they answer all our questions. But according to LeCun's recent synthesis of world model research, being highly useful in a chat window is fundamentally different from being a robust, intelligent agent that can actually act in the physical world.
All right, so here's our roadmap for today. We'll be looking at the limits of LLMs, two crucial capabilities they're missing, the teenage driver test, the new JEPA architecture, and we'll wrap things up by looking at what all of this means for AI safety and sovereignty. Let's get right into it.
Okay, part one. The limits of LLMs. We really need to address the elephant in the room right off the bat. LLMs are incredibly useful, sure, but usefulness does not mean they are architecturally complete. See, language, math, and code, they're all neat, discrete symbolic systems. An LLM generates its next output basically by guessing from a set dictionary. And for text and code, that's fantastic. But the real physical world is continuous, it's incredibly noisy, and it's totally unpredictable. An architecture that is built literally just to predict the next word is simply not equipped to navigate that messy reality. And this brings us to a massive paradigm shift. Think about it. We are trying to pivot from machines that just guess the next word based on statistics to machines that actually understand how the world changes when they interact with it. An LLM learns patterns and symbols, but a real agent, it needs a causal, predictive model of how things, tools, bodies, environments interact across time. Moving on to part two. Two missing capabilities. What exactly do agents need that LLMs just don't have? LeCun points out two huge glaring gaps. First, predicting consequences. A true agent absolutely has to estimate what happens after a physical action. LLMs just predict tokens. They don't predict real-world state transitions. And second, planning through explicit optimization. Pumping out text that looks like a plan, yeah, that is not the same as actively evaluating and choosing physical actions to minimize costs. LLMs sort of fake planning by generating tokens, but they completely lack a true mechanism for evaluating actions based on future states. All right, part three, the teenage driver test. Let's ground this with a real-world example to show just how massive this data efficiency problem really is.
Think about this for a second. It only takes a human teenager about 20 hours of practice to learn how to drive a car. Just 20 hours.
Now, compare that 16-year-old to our absolute most advanced AI. Autonomous driving systems have devoured millions upon millions of hours of driving data. And guess what? They still struggle to deliver unconstrained level 5 autonomy. This stark contrast really hits the nail on the head. Pure imitation learning from huge piles of behavioral data is wildly inefficient. So why does the teenager win? Well, because they sit down in the driver's seat with a rich, built-in world model. They already intuitively get physics. They know a heavy object takes time to stop. They get object permanence. If a car drives behind a truck, they know it didn't just vanish into thin air. They understand social expectations and risk. Those 20 hours of driving lessons are really just fine-tuning a brain that already understands how the world works. But a purely imitative AI is trying to learn all of that from scratch, strictly from behavioral traces. No wonder it struggles. Which leads us to part four, JEPA and world models. If brute force imitation isn't the answer, what is the architectural solution to building a machine with actual common sense? Enter JPA, or Joint Embedding Predictive Architecture. This is a non-generative, self-supervised method. And the real game changer here is that it focuses on predicting high-level concepts instead of getting completely lost in the weeds of sensory noise. So rather than trying to perfectly recreate the exact raw pixels of an image or video, a JPA simply predicts the abstract representation of those pixels. To put it into perspective, imagine you're crossing the street. You don't need to perfectly predict the exact reflection of sunlight on the bumper of an oncoming car or the texture of the leaves blowing in the wind on a nearby tree. Doing that kind of pixel-level prediction takes massive, wasteful computing power. Representation-level prediction, which is what JEPA uses, only focuses on the variables that actually matter for the task. Things like identifying the vehicles, checking their motion, and anticipating their expected trajectories. So when you condition a JEPA on actions, it basically turns into a world model that can explicitly plan. It's a very logical, step-by-step process. It encodes the present state, imagines a few candidate actions, and then predicts the future states that those actions would create. After that, it scores those futures based on things like safety or effectiveness and picks the optimal route. This right here is what LeCun calls objective-driven AI.
But hold on, there is a pretty massive catch when you're dealing with abstract concepts instead of exact pixels. What happens if the AI just decides to take the lazy route and cheat? This is a critical problem known as representation collapse. Imagine if the AI maps every single image it ever sees to the exact same constant value. Let's say the number 0. Well, then it can flawlessly predict that the next state will also be 0. It scores a perfect 100% on its prediction task, but it has learned absolutely nothing about the real world. Overcoming this trivial failure mode is basically the central challenge of the entire JEPA project.
Thankfully, researchers have come up with some really clever ways to force the AI to learn real, meaningful differences. Older methods relied on complex contrastive systems to pull positive pairs together and push negative ones apart. But the exciting new frontier, it uses distributional regularization. These are elegant mathematical rules that naturally stop the system from taking the easy way out, replacing messy hacks with clean geometry. And the best part? This isn't just theoretical whiteboard stuff anymore. Recent papers like the World Model are proving that these architectures can actually achieve end-to-end planning straight from raw visual data. Using next embedding prediction, it's claiming faster planning speeds than some foundation model-based setups. It totally shuts down the critique that JEPA is just some abstract idea for learning representations, proving it absolutely works as a real control architecture.
Finally, let's jump into part 5, safety and AI sovereignty. Why does this architectural shift matter on a global scale? Well, LeCun argues that LLMs are intrinsically unsafe when you try to use them as physical agents. Why? Because their core objective, just predicting the next token, doesn't have any hard guarantee of truth. If you take an agentic LLM and plug it into physical tools or critical infrastructure, it might execute an action simply because a similar string of text appeared in its training data. It has literally zero understanding of the real physical consequences of what it's doing. That is exactly why objective-driven AI is such a safer alternative to unconstrained generation. Instead of just crossing our fingers and hoping an autoregressive prompt spits out a safe action, objective-driven AI explicitly predicts outcomes. It gives us a much more inspectable system where strict safety constraints can be hard-coded mathematically right into the optimization process itself. Look, it's not a magical fix for all risks, but it ensures the system is actually trying to minimize harm, rather than just generating plausible-sounding text. And this control issue goes way beyond just physical safety. It extends to global culture. LeCun outlines this concept called the Tapestry Initiative, which tackles AI sovereignty. The reality is, much of the world doesn't want its information diet completely mediated by proprietary systems built in California. The Tapestry Initiative pushes for a federated approach. Local institutions keep their raw data completely private, sharing only parameter updates to help build a global foundation model. Then, local actors can fine-tune that model to actually fit their own unique languages, laws, and cultural values. So just to quickly summarize where the industry stands today, autoregressive LLMs are totally dominant commercially, but they lack physical grounding. JEPAs offer highly efficient planning, but they're mostly still in the research phase. The true engineering frontier, the big next step, is the objective-driven agent, a system that can finally optimize physical action sequences with explicit built-in safety guarantees. Which leaves us with this final thought. As we transition from simple chatbots to physical robots and infrastructure, if the future of AI relies on explicitly modeling the physical worlds and defining safety objectives, whose world model will we ultimately be living in?